Hello, good evening, my dear student friends. Again, welcome to PG Physics classroom for nuclear specialization students. Yesterday, we discussed the beta disintegration process. So, how the beta will disintegrate in terms of three processes, that is beta negative, positive, and as well as by electron capture process. And also, we calculated the disintegration energy for particular beta positive, negative, and electron capture process. Now today I am going to discuss with you people that the origin of beta spectrum. Today's topic is very important one, and also we are going to discuss that is polyneutrino hypothesis, which is also very important topic regarding to this unit, that is beta decay unit. So I am just opening the file, please wait for a while. Okay, 39. Okay, so yesterday we discussed that is beta disintegration energy, how to calculate. So now let us start with origin of continuous beta spectrum, that is what the neutrino hypothesis. The secondary electrons, as you know, the decay scheme of every element, for example cesium 137, barium 133, sodium 22. Likewise, the decay process also happens for the beta elements. For example, in our laboratory we are having only one beta source, that is thallium 204. Here the secondary electrons giving rise to the discrete peaks are not emitted from the beta disintegrating nuclei. Only the electrons in the continuous part of the beta spectrum are emitted during beta disintegration of the nuclei. Okay, so this is okay. We'll open another file. See here, I am showing the figure here, that is beta transition between two discrete energy states of the parent and product nuclei, showing apparent breakdown of conservation of energy. See, continuous beta energy distribution, that is the energy is going to be distributed continuously, not discrete in the manner what then that is not continuous in nature, that is incomplete in nature. The area under the continuous distribution graph, which shows that the number of secondary electrons forming the peaks is only a few percent of the total number of beta particles emitted. Careful measurements have shown that the total number of electrons, including those in the peaks as well as in the continuous spectrum, is slightly greater than the number of nuclei undergoing beta decay. Okay, so this is not necessary. So okay, both for beta negative and positive decays, the emitted beta particles are found to have continuous distribution of energies or velocities ranging from 0 up to a maximum. Energy as well as the velocity distribution is continuous in nature in the process of beta negative and beta positive decays. So in the case of electron capture, no observable particle is emitted from the nucleus. Only X-ray photons or Auger electrons, characteristic of the product atom, are observed, as you know. So what is meant by Auger electron? For example, the nucleus which exists in the center of the atom, the electrons are revolving around the nucleus, that is K, L, M, N, like that in that orbits. When some amount of energy is impinged on the particular atom, the electron is removed from K shell or L shell depending on the binding energy. The vacancy is created. That vacancy is filled through the transition from higher orbit to lower orbit. During the transition, the amount of energy will be liberated in the form of radiation. So that is known as radiation. So that may be X radiation or gamma radiation. But in some other cases, what happens? The radiation will not emit. The electron is ejected out. That electron is called as what? Auger electron. Now, we have seen before that during beta disintegration the mass number remains unchanged while the atomic number changes by 1 unit. This means that either a neutron is changed into a proton or a proton is changed into a neutron, so that the total number of protons and neutrons remains unchanged. So as already we discussed in yesterday, so experimental study of alpha disintegration shows that the alpha particle spectra are discrete in nature. Okay, see here, alpha disintegration shows that the alpha particle spectra are discrete in nature while the beta particle spectra are continuous in nature. Please do remember. So which points to the fact that the nuclei exist in the discrete energy states as expected from quantum mechanics for a closed microsystem. Transitions between these discrete levels in the parent and product nuclei gives rise to the emission of monoenergetic groups of alpha particles, as you can see in the alpha disintegration process in this book only, that is S.N. Ghoshal book. The same conclusion is drawn from the study of gamma ray spectra. We will discuss in later after completing the beta emission. It may therefore be expected that due to the transitions between such discrete energy levels in the parent and product nuclei in the beta decay process, the beta particles will also be emitted with one or more definite energies given by the energy difference between the initial and final states, less the mass energy of the beta particle. However, the observed continuous distribution of the beta energies contrary to this expectation. Thus, there is an apparent breakdown of the principle of conservation of energy in the case of beta decay, as shown in figure 5.12. So, that is, the energy will not be conserved. Then, before decay and after decay, energy remains unchanged, but it changes. It may, however, be noted that the beta disintegration, so as we defined in earlier class, with the mass energy difference between the parent and the product nuclei less the electron rest energy for both beta negative and beta positive disintegrations, which also equals the maximum energy E of the emitted beta particles. Okay. Another puzzling feature about the beta decay is the apparent failure of the principle of conservation of angular momentum. First one is there is a failure of conservation of energy. Here again the failure of conservation of angular momentum. We know that the protons and the neutrons constituting the nucleus of an atom have intrinsic spin angular momentum. If the total number of nucleons is even, then the total spin angular momentum of the nucleus is either 0 or integral. On the other hand, if A is odd, then S will be half odd integral. In addition, the nucleons may have orbital angular momentum, which can only be integral multiples of h cross, since the total angular momentum of the nucleus is I is equals to L plus S. As you know, the value of I is integral or half odd integral in units of h cross, depending on whether the number of nucleons in the nucleus is even or odd respectively. For example, if A is even, so then I is integral or 0. So in the beta disintegration process, since A remains unchanged, I will remain integral or 0. That is, either I does not change or changes by an integral multiple of h cross. Similar in the case when A is odd. Okay. We will next see. So now the electron has an intrinsic spin half. So during its emission from the nucleus, it can carry away half odd integral unit of angular momentum, since the orbital angular momentum changes. If changes any can take place by an integral multiple of h cross, this means that the emission of an electron from a nucleus should change the angular momentum by a half odd integral multiple of h cross, which however contradicts the statement made above that in the beta disintegration process I should change by an integral multiple of h cross. To explain these apparent inconsistencies, the Pauli in 1930 proposed that at the time of beta decay of a nucleus, a hitherto unobserved second particle in addition to the electron is emitted, which carries away the balance of energy. So that is E nu. So E nu represents energy of the hither neutrino is equals to Em minus Eb. so that the total energy of the two particles is equal to the maximum beta energy when the electron is emitted with zero kinetic energy. The second particle is emitted with the maximum energy, EV is equals to EM. On the other hand, when the electron is emitted with the energy equal to maximum energy, then the other particle has energy E nu is equals to 0. See here, once again I will repeat. The Pauli proposed that at the time of beta decay of a nucleus, during the beta decay process, a hitherto unobserved second particle in addition to the electron is emitted, which carries away the balance of energy. That energy is equals to EM minus maximum energy minus beta energy, so that the total energy of the two particles is equal to the maximum beta energy. When the electron is emitted with zero kinetic energy, then second particle is emitted with the maximum energy, EV is equals to EM. On the other hand, when the electron is emitted with the energy EM, so then other particle has energy EV is equals to 0. Here we have neglected the energy of the recoil nucleus undergoing beta decay, since it is much heavier than the particles emitted. This new particle proposed by Pauli has been named the neutrino. That is, hence we call it as a Pauli-neutrino hypothesis. In the beta decay process, the electron is ejected. In other case, some unidentified particle is also liberated with different energy, with the different mass. That the Pauli has been named the neutrino. It must have such physical properties that it would be very difficult to detect it. In fact, it eluded observation for more than 25 years after Pauli had proposed the neutrino hypothesis. See, he has done the experiment to detect the neutrino particle. So he took time to detect such particle about 25 years. Later he proposed the Pauli-neutrino hypothesis. We can guess about some of the properties of the neutrino. So this is important, please do remember. So in annual examination they may ask for 4 to 5 marks, list out the properties of the neutrino. The neutrino must be electrically neutral, so that the only change in the charge of the nucleus during beta decay is due to the emission of the electron or positron, or due to the capture of an orbital electron. This is in agreement with observation. First property is what? The neutrino must be electrically neutral. Second one, the mass of the neutrino should be 0 or very nearly so. This follows from the fact that the maximum energy of the emitted electron is equal to the mass energy difference between the parent and the product nuclei less the rest energy of the electron. If the neutrino had a finite mass, then its rest mass energy must also be subtracted to get maximum energy. So hence we consider that the mass of the neutrino should be 0 or very nearly so. So third one is intrinsic spin of the neutrino should be 1 by 2. The spin of the neutron particle is 1 by 2. Since the electron spin is also 1 by 2, two spin half particles are emitted during beta decay. Hence the two together will take away an integral unit of angular momentum. So which is in agreement with the statement made above regarding the change of angular momentum in beta decay. The neutrino must obey Fermi-Dirac statistics like the electron, since its spin is 1 by 2. So the neutrino must obey the Fermi-Dirac statistics. The four properties of neutrino you can see here. So it must be electrically neutral, it should be 0, the mass of the neutrino should be 0 or very nearly so, and intrinsic spin of the neutrino should be 1 by 2, and this neutrino must obey Fermi-Dirac statistics, because electron obey the Fermi-Dirac statistics, which is having the spin 1 by 2. Now Enrico Fermi, the famous Italian physicist, was the first to work out a successful theory of beta decay based on the neutrino hypothesis. So that is what we are going to discuss with Fermi's theory of beta decay. The famous Italian physicist was the first to work out successful theory of beta decay based on the neutrino hypothesis. According to Fermi, beta decay occurs due to the transformation of a neutron into a proton inside the nucleus with the emission of an electron and an antineutrino, which is the antiparticle of the neutrino, just as positron is an antiparticle of the electron. You can see the equation number 1 and write it down, the equation 5.61. So here neutron is converting into a proton with emitting an electron and also the antineutrino. Electron is antiparticle of positron and antineutrino is antiparticle of neutrino. Such decay is actually observed in case of a free neutron, which has a half-life of 10.6 minutes when it is outside the nucleus. You can refer, that is 5.13 section. The reverse transformation of a proton into a neutron by the emission of positron and a neutrino also occurs inside the nucleus in beta positive decay. See here the conversion of proton to neutron. Here what happens? The positron and neutrino will be liberated during the beta positive decay, but in the beta negative decay the antiparticles are get ejected. However, this transformation cannot occur in case of a free proton because energy conservation cannot be satisfied in this case, the proton being lighter than a neutron. It may be noted that electrons, positrons, neutrinos and antineutrinos escaping from the nucleus in beta decay do not exist initially inside the nucleus. They are born at the time of beta decay. Getting my point? Please do remember here. It may be noted that the electrons, positrons, neutrinos and antineutrinos escaping from the nucleus in beta decay do not exist initially inside the nucleus. They are born at the time of beta decay, just as the photon is born at the time of radiative transition in an atom. So this is unlike, this is, wait, okay. This is unlike the case of alpha decay of a nucleus, since the two protons and two neutrons forming the alpha particle already exist inside the disintegrating nucleus. But in case of beta decay process, electrons, positrons, neutrinos and neutrinos have been observed during the decay process. But in case of disintegration of alpha decay, protons and two neutrons exist in the nucleus itself. Unlike alpha decay, which takes place only in the heaviest nuclei, beta decay can occur in a wide range of nuclei, starting from the lightest at A is equals to 1 up to some of the heaviest nuclei known in nature or artificially produced. Alpha decay happens for only the heavier elements. Beta decay happens for starting from the lightest to highest. A is equals to from the 1 up to some of the heaviest nuclei known in nature or artificially can be produced. The energy liberated in beta decay process also varies over very wide range. For example, in decay of tritium, so tritium is converted to tritium, beta negative decay, the decay energy is only 0.02 MeV, while the decay that is boron, which converting to carbon, beta negative decay, it is having the energy 13.4 MeV. So a brief sketch of Fermi's theories of allowed beta decay will be given in. It gives a mathematical expression for the energy distribution of the beta particles. See, I hope okay, we'll discuss soon. So please read it out, whatever I discussed today, read up to this much, that is 13.4 MeV. So later again we will start with the detailed description of Fermi's theory of beta decay. I will send you soon this video. Okay. Thank you for your cooperation. Please do watch the videos, and if any queries, any doubts, you can post the question in the WhatsApp number. So I don't know some of you are having my number or not. If you are having, you just send me the questions, or else you can call me directly. I will tell you how to read and how to prepare a notes. Thank you. Bye.